Good afternoon everyone, and welcome to the first video of this multi-part series for the B200 project. This is a part of a multi-part video series of the B200 clock, B200 being short for base 200 clock. So a bit of a side project of mine to learn a bit more about modeling within Inventor and combining some mechanical elements alongside the electronics to build a functional clock with a few different complications or ways to view the representation of time and the progression of time. The clock itself is composed of the top and bottom enclosure with the time indicated by this internal disk assembly here. This is actually made from old mechanical hard drive platters, and you'll also see a smaller indicator needle here at the bottom. And this disk is allowed to move from the bottom to the top of this enclosure, a total distance of about 450-460 millimeters. But once you account for the additional tolerance and the space requirements for the different components, you have a usable travel distance of about 400 millimeters, and with a pitch of 2 millimeters per step or per turn rotation of this TR10 lead screw, you get a total of 200 steps. So base 200 will be 200. And this disk assembly, as it moves up and down, gives you an indication of the current time or measurement position, moving from the bottom all the way to the top. And the way that this functionality is implemented is quite a bit different than a traditional lead screw implementation. So this hard drive assembly over here, we've got some plastic spaces between these three aluminium discs from the old hard drive platters, and surrounded by this ring here on the outside. And you'll note there's 4 small little magnets, one on each of these corners, that's allowed to freely traverse vertically along these support struts. So again, also this will be 3D printed, and you'll note there is a bit of an air gap between this hard drive assembly and the outside ring, which I'll refer to as the clutch. And if you have a closer look at this hard drive assembly, if I go ahead and double click on that and we do a bit of a section view, you will notice that on the inside our spaces as accommodates 4 high-strength neodymium magnets. There's one spacer disk located here, as well as one in the adjacent section over here. These magnets have the same polarity all around. The disk in the bottom is slightly offset, so if I just rotate between the two, you'll see the magnets jump around a little bit in terms of their position. And the reason for this is to ensure that we have a magnetic field, and when this disk is in this position relative to the magnetic clutch here on the outside, there is an attractive force between the hard drive disk assembly and these magnets. And as the stepper motor, which is located down in the bottom enclosure, tries to drive this lead screw, instead of the disk just freely rotating, we have a force by means of magnetic attraction between this clutch and the hard drive assembly. And as the disk just tries to move along with this lead screw due to some amount of friction between the lead screw and the hard drive assembly, we have these magnets actually holding the disk back. And this allows the disk to start traveling along the length of the lead screw. And because this magnetic clutch is also allowed to move freely in the vertical direction, it will move along with the disk. So a contact-free system using magnets looks quite elegant, and we can 3D print all of the components as well as recycle some old hard drive platters, and this will allow the assembly to traverse up and down to provide an indication of time. So the top and bottom enclosures also designed to be 3D printed to house all of the electronic components, supported by 4 carbon fiber rods. These are about 12 millimeters in diameter, the outer ones, 5 millimeters the inner ones, and these outside supports are hollow on the inside, so around about 10 millimeter inner diameter, which allows for passing through of some wires to the top and bottom enclosures. And in addition to that, there's a 24 LED NeoPixel ring down here in the bottom, as well as the top, which we can use for general illumination or to provide another indication of the current time or measurement being performed. And the light coupled with these old magnetic hard drive discs will give quite a cool illumination effect with the lights coming down and bouncing off of the discs. But the entire assembly doesn't just stand empty as visualized over here. If I turn back on the visibility of the surrounding cylinder, the plan is to install a acrylic or perspex type of cylinder on the outside, so it gives this sort of hourglass appearance, prevents dusts from settling on the inside, and should also allow for very smooth and quiet operations with additional sound insulations. The stepper motor is not operating at very high speed, and the stepper driver is also selected to be particularly quiet, so to give a very sort of calm and low volume operation. So you'll just see this disk assembly move up and down as the stepper motor moves, and this needle indicator dial also providing a more in detail view of any slow progression, given that we can have very fine control of the stepper motor to really see the progress as the entire assembly rotates. In addition to that, you'll note that there's a small little gap here, so I'm just gonna turn this off again. There is a small distance sensor located down here in the bottom, which is triggered when there's an obstacle or an obstruction around about 50 millimeter away from the sensor. So in order to calibrate this, this clock assembly, we have this needle moving over this distance sensor, and we'll sort of get a square wave output every time the needle traverses the sensor down here, up until the point. So let's say for the calibration process, we can move this disk all the way down. When the disk is in a low enough position, this distance sensor will provide a continuous trigger regardless of this needle position, and thus we'll know that the disk assembly is approximately 50 millimeters away from the bottom. Even if we turn the lead screw enough times that the disk assembly does make contact with the coupler and the needle above here, due to the design of this magnetic clutch, you will not be able to damage any of the mechanical components, as the disk will just start slipping from the magnetic clutch, as there's a limited amount of force or torque that this magnetic attraction can support before slip starts occurring. We'll just have to make sure that the magnetic clutch over here doesn't fall down all the way to the bottom and we lose contact with the hard drive assembly up here, but that can be done quite readily with some spaces over here. So the clock is designed with sort of a forward-facing side over there, as well as a backside that is sort of a bit more of a clean look or feel for it, without all of the buttons and controls and display items. If we roll back around here to the front, we've got a 16:2 character LCD display to provide some general information. Here on the top, adding a gesture sensor, so instead of physical or mechanical buttons, we can use gestures to control the menu, what sort of time is being currently displayed, turn some settings on and off. And then down here in the bottom, we have a general power switch to activate the entire system. We've got a potentiometer to control the brightness of these LED rings here on the inside and the top. And note that the LED rings, we can provide exactly the same sort of visual design or pattern of LEDs as long as they are mirrored, with the one facing down and the one facing up, which we'll do later on in software. And then we've got two standard DC barrel jacks to connect a 12-volt input source of up to a maximum of 2 amps, with the majority of the power going to the illumination of the LEDs. With the stepper motor only needing to drive the magnetic clutch, not a lot of power is really required to control the entire system, with the remainder of the power going to two Arduinos. So why two Arduinos? The design of the system is such that we have a primary logic controller here at the top and a secondary microcontroller for the bottom in the form of an Arduino Nano and an Arduino 33 IoT here on top. And the logic controller will be responsible for driving the menu system, reading the various sensors, setting the real-time clock, and will determine exactly where the position of disk assembly should be. The Arduino in the bottom, communication taking place over serials, so just two copper wires that connect the two Arduinos, sort of a generic code-based communication system similar for standard 3D printers. We can send some commands down from the logic controller and down to the stepper controller to say be at position X along the length of the lead screw. And the Arduino at the bottom uses the Excel stepper library, which is a very easy to use stepper controller library to set positions either absolute or relative to a homing position, to enable or disable the motor assembly. So a very nice library you can use to control the stepper motor. So as the positions are continuously communicated down to the stepper controller, if that is the only responsibility for that microcontroller, all cycles and computational power goes towards having a smooth operation of the stepper motor for continuous smooth operations. But also the stepper controller, microcontroller down in the bottom, we can also relay things such as the temperature or the battery voltage. We'll have a battery backup down here. That pieces of information can be communicated back up also to the microcontroller, and also handshake messages. Once the logic controller sends down a message for the stepper motor, is there a corresponding return message that acknowledges that command to make sure that the system is operating as designed. If we take a sectional view from the side over here to see what the internals sort of look like, space that a little bit more. So starting at the bottom, we have the stepper motor over here with some tolerance to allow for a lid to fit nice and snug on top of the enclosure, with some bolts coming through to affix that to the body of the enclosure, and then enough space for a PCB or variable to mount all of the electronics, as well as all the voltage control primarily takes place down here. So 12 volts for the Arduino and the stepper motor, but the LED lights, for example, needs 5 volts, so we'll add another regulator for that. We can also pass along that 12 volt to the Arduino Nano 33 IoT sensor sitting up here, which interfaces with all of the primary sensors for temperature, barometric air pressure, the real-time clock. There's also a ROM chip included to record user settings, so non-volatile storage for just general settings for information to save, uptime, etc. And there's a bearing on top here to support the lead screw here as well. Optional distance sensing is included here as well, but after running through the design process and reviewing all of it, it might not be necessary to add the secondary distance sensor up here, but it's included nonetheless if we want to ensure that for a specific position the disk must not be within the detection zone, otherwise we know that the clock is no longer properly calibrated for that. And then moving a little bit deeper with this section view, you'll note that the struts or the support rods over here, we'll leave a bit of an opening space for the for the wires to pass through. So that's the 12 volt and the serial connection wires, and even perhaps 5 volt for the LED ring up here. I'm just trying to draw this section. There we go. So one of the support struts can be used to pass through wires, whilst the other one over here is designed with a bit of a slot, which we can drill a hole through the strut to put a bolt through, so the entire assembly stays fixed and in place. So in terms of setting the time, you can do that either manually using the menu interface control system, but the Nano 33 IoT, with its capability to connect to Wi-Fi, we'll utilize that to synchronize the real-time clock to a N-trip server that provides us with pretty accurate timekeeping. And we can also include things such as UTC offset for different time zones to be included as well. Note the bottom cover plate over here includes plenty of air ventilation in the event that we do need that for some heat from the stepper motor, but in testing the stepper motor consumes very little power, down in the 2.5-3 watt range, and then space also for a rechargeable lithium ion battery for some measure of wireless operation. With the low power consumption, we expect around about an hour and a half of operation of the battery, with automatic switch over back to its primary DC power source. So either in the event of a power failure or for a bit of a mobile demonstration, the B200 clock can still serve its functionality. So that's it for the 3D modeling component. Still in the process of 3D printing all of these different components, give a bit of a demo once the hardware has arrived, and also planning to add some nice finishing touches in the form of some gold leaf, just to add to some of the reflectivity of the LEDs, perhaps inside of where the acrylic tube will be, to gold leaf all of that to aid with the reflection of the various lighting, the LEDs on the top of the top and bottom, so reflecting off the mechanical disc, refracting into the acrylic, as well as reflecting back from the gold leaf over here. So it'll sort of function as a little nightstand for additional illumination. So that's it for the 3D modeling overview. In the next section of this video, I'll provide an overview of the different different complications and how exactly this positioning system functions for the lead screw and the disc assembly. So let's quickly switch over to the calculation page for that in Excel. So currently the usable length of the lead screw is approximately 400 millimeters with about a tolerance of 5 millimeters in the final design. And then the steps per lead screw, so if the lead screw were to turn for the entire 400 millimeters, we have 2 millimeters of pitch for the lead screw, which means you can rotate 200 times from the top to the bottom, hence the name the B200 clock. For the stepper motor, you can turn the stepper motor, so for full step, it's 1.8 degrees per step, which is 200 steps of the stepper motor per rotation of that lead screw. And since we can rotate this lead screw 200 times for the disc to move from the bottom to the top, and we can return the stepper motor 200 steps per rotation, if we multiply the two, we have 40,000 steps of the stepper motor to move that disc assembly from the bottom all the way to the top without any microstepping considerations. So using the 2208 stepper controller, it's a pretty relatively new controller, very silent operation with very good interpolation to give that smooth movement but also reduce the amount of noise. We can do up to 16 microsteps per step for the stepper motor. So for 40,000 full steps times 16 microsteps per step, we can get a total of 640,000 steps per distance over the entire length of that lead screw. So pretty fine control to indicate a measure of time or anything else with the requisite resolution. So let's consider 24 hours in a day. We have around about 86,000 seconds in a day. If we divide that number by the total number of steps that we can use with this design, we get around about every 0.13 seconds we need to add another microstep to move that disk assembly, or the inverse of that is 7.5 microsteps per second. So you should see the slower progression of the needle down in the bottom as it turns, and then the slow progressive movement of the disk assembly from the bottom to the top. So at midnight or just after midnight, the clock will move down to its homing position in the bottom. Let's give a bit of visualization for that. So down in the bottom, just after midnight, then we go up, sunrise, noon, late afternoon, up until the evening, and then the clock reverts back down when the cycle starts again. And per screw rotation, or when the needle will make a full rotation, it's about 3.6 minutes. So it should still be viewable as a continuous smooth motion, but as a fraction of the entire length of the screw, that will indicate the progress of the duration of a full day. So moving on to the different complications, there's 5 complications in total. The first complication is, or rather let's start with the moon phase one here in the middle. So a given moon phase for the 21st century, on average, if you're going to do that calculation, it's about 29.530266 days, if you want to be very accurate. And that corresponds to every 3.78 seconds, we need to do 1 microstep to indicate the whole phase of the moon. So the hard drive assembly will move from the bottom when it's a new moon. A full moon will be indicative of the disk assembly sitting in the middle, maybe with some cool visualization of the LEDs, and then all the way to the top again as we approach another full moon over there. So it takes 28 days for the disk to go from the bottom all the way to the top. So that's for the moon phase. Then moving on to the year clock, if you want to view the year as a representation, there's about, let's just get the commas there correct, 31.5 million seconds in a year. So that means every 49 seconds we need to do one microstep. And for the linear screw, that means that every 21.9 hours, our assembly or the disk will actually move by 1 millimeter upward. So at the start of the year, we start at the bottom, and as the year progresses, it goes all the way to the top. We can take this even to the extreme if we want to see the progression of an entire century. So if the century ticks over, we start the assembly at the bottom, and on year 99 it will be roundabout at the top. It means that we need to do one microstep every about 1.5 hours, and it takes a full 90 days for the assembly to move 1 millimeter linearly upward. But incidentally, that means for every year we will have to do 2 complete rotations. So the needle in some measure will actually be an indication of the seasons. So if this needle needs to rotate twice annually, we can use that to sort of read off the seasonal change as well. So again, the number 200 comes in handy for different representations of times or the progression thereof. Then we can also start adding some sensor functionality. So there's a temperature sensor and an atmospheric or barometric air pressure sensor included. And the temperature sensor is a 0.1 degree centigrade accurate temperature sensor. So it senses changes in temperatures very readily. Whereas the air pressure sensor is also quite sensitive. I believe it's something like 25 millimeters of air pressure. So if you physically lift the sensor, you can note a change in the air pressure. So that also makes it sensitive to different types of weather patterns, and is then ideal to serve as a barometer for weather changes. And then to think a little bit about the implementation of a sensor like this, every time you go into that mode, the disk will actually zero in the center, so any increases in air pressure can be observed as well as any decreases. So the full scale of the temperature sensor, it's going to be 50 degrees centigrade, which means that we need to perform almost 13,000 microsteps per degree centigrade, or then put differently, for every eighth of a degree centigrade, the assembly will move by 1 millimeter linearly up or down. And the LEDs, since there's 24 LEDs, if we make them say red for anything above 25 degrees, which can be the midpoint, if it's going all the way just full red LED circle, that goes to say 50 degrees. And again, starting 25 degrees neutral, and we go down and it gets progressively cooler, we can make the LEDs go blue. And once the entire ring is lit up, 1 LED per 1 degree centigrade, once it's fully blue, we know we'll be at 0 degrees C. So it can feature as a nice thermometer. And then the same for the atmospheric range. It means that the resolution is that for every 125 millimeters or 0.125 meters of air pressure change, the needle assembly will move by a millimeter up or down. And again, any minor variations in this atmospheric air pressure, you'll continuously see the needle slowly updating as the air pressure continuously changes in the atmosphere. And again, a 50-meter range will give more than adequate range for the atmospheric temperature range, whether that be moving up and down of stairs or an elevator, or then the different weather patterns as well. So that's an overview of the B200 clock and its functionality, different CAD models. So currently in the process of 3D printing the enclosures, as well as testing all of the electronics, which will be a separate video once we start assembly with that, as well as the final implementation of testing the B200 clock. So let me know down in the comments if you have any questions or queries. Little side project of mine. Hope you guys learn something from it, get a few ideas from this project. More than willing to share it, and planning to put the resources, models, and code available at some point for anyone to use. Thanks for watching. Until the next video, cheers.